we're going to do more examples today. So let's just find the series S equals the sum of 1 over n minus 1 over n plus 1. This time n starts from 1, okay, as usual. So if you write this series uh, explicitly, then you're going to get the 1 over 1 minus 1 over 2, okay. Remember, when you n equals 1, you get 1 over 1 minus 1 over 1 plus 1, which is 2. That's 1 over 1 minus 1 over 2. And the next term, you take n equal to 2, so you get 1 over 2 minus 1 over 2 plus 1, which is 3. And so on. You get the next term for n equal to 3, so you get 1 over 3 minus 1 over 3 plus 1, so that's 1 over 4. And then the next term will be n equal to 4, so you get 1 over 4 minus 1 over 4 plus 1, which is 1 over 5. So we get the series like this. So if you see the second term of the second part of each term will cancel the first part of the next term. Like in the first term, you get negative half as the second part, and you get a positive half in the second term as the first part. So they cancel each other, and then the second part in this second term is negative 1/3, and it will cancel the first part in the third term, which is 1/3, and the second part in the third term is negative 4, and it will cancel the first part in the fourth term, which is positive 1/4. So you can rearrange the terms in the way, you know, like this. So you get a lot of cancellations, right? So basically, what is left is just 1 and the last term. If you um, try to compute the partial sum, okay, the partial sum. So S sub n, so that means you add the first n terms of this series, okay. So you get the last term as 1 over n minus 1 over n plus 1 in this partial series, or partial sum. And then you rewrite this sum by the way I just said, and then all the terms in between are crunched. And what is left is just the first term, which is 1, and the last term, negative 1 over n plus 1. And then to find the sum of the series, or the infinite series S, you just take the limit for S of n with n approaching infinity. Okay, that means you include all the terms in the sum, right? The partial sum. Okay, so that's 1 or 1 minus 1 or plus 1. So as n approaches infinity, then you got the second term equal to 0. That has the 0 as the limit. Okay, you got the huge number in the denominator. So the actual sum is 1. Okay, 1 minus 0 is 1. So this is a series called the telescoping series. It's just like a telescope. When you can extend it and compress it. So all the terms in between are crunched, basically, when you compress the telescope, right? So that's another type of series. All right. So we can take a look at some more examples of telescoping series, and sometimes this kind of series are written in a format that need to be rewritten. Okay, so in this series, S equals the sum of n equal to n from 1 to infinity of 2 over 4 squared minus 1. So the first thing you need to is to break up the term of 2 over 4 and square minus 1 into 2 by using partial fraction decomposition. Okay. So let's just rewrite the 4n squared minus 1 as 2n to the square minus 1 square. Okay. And then you can use the difference of two squares to factor it as 2n minus 1 times 2n plus 1. It's easy. And then, the partial fraction decomposition means you can rewrite this term of 2 over 2n minus 1 times 2n plus 1 as two terms with two different denominators in here. Namely, you can have a term of a over 2n minus 1, and you get another term of a over 2n plus 1. And then a and b are just some numbers that you need to figure out, okay, from the original expression 2 over 2n minus 1 times 2n plus 1. And you can easily solve for a and b, and you're going to get a equal to 1, b equal to negative 1. All right. So then we have 2 over 4n squared minus 1 equals 2 over 2n minus 1 times 2n plus 1 equals 1 over 2n minus 1 minus 1 over 2n plus 1. And you can easily check it by taking the difference of these two terms of 1 over 2n minus 1 and 1 over 2n plus 1 using the least denominator. You can double check that is the right the decomposition. Okay, so then we got the partial sums. Okay, s sub n. Just do it again. You just add all the first n terms. So now the terms can be written as 1 over 2n minus 1 minus 2 over 1 minus 1 over 2n plus 1. So again, you take n equal to 1, you get 1 over 2 times 1 minus 1. Okay, so 2 times 1 is 2, and 2 minus 1 is 1. So you get 1 over 1 minus 1 over 2 times 1 plus 1. So 2 times 1 is 2, 2 plus 1 is 3. So that's 1/3. So the first term of this series is actually 1 over 1 minus 1/3. And then you take n equal to 2. Plug in 2 for n, you get 2 times 2 equal to 4. 4 minus 1 equal to 3. So that's the first term in the denominator. And then 2 times 2 is 4. 4 plus 1 is 5. So that's 1 over 5. So 1/3 minus 1/5, that's the second term. And then n equal to 3, you just do that again. 1 over 2 times 3 minus 1. So 2 times 3 is 6. 6 minus 1 is 5. So that's 1 over 5. Minus 1 over 2 times 3, which is 6 plus 1. And so that's 7. So you got 1 over 5 minus 1 over 7. And then you take n equal to 4. So 1 over 2 times 4, you get 8. 8 minus 1 is 7. So that's 1 over 7 minus 1 over 2 times 4, which is 8. 8 plus 1 is 9. So that's 1 over 9. So you get 1 over 7 minus 1 over 9. And then you just add up to n. So, the last term will be 1 over 2n minus 1 minus 2n plus 1. And the term before that will be 1 over 2n minus 1 minus 1 over 2, 1 over 2n minus 3 minus 1 over 2n minus 1. If you plug in minus 1 for n, okay, in the formula. And then again, you can cancel the negative 1/3 and the positive 1/3, negative 1/5, positive 1/5 and negative 1/7, and the positive 1/7, and so on. So everything canceled except for the first term and the last term. That's always the case for telescoping series. So that's again a telescoping series. So we got 1 minus 1 over 2n plus 1 at the end. And then you just take a limit of these partials. You include all the terms in this series. So that's the limit of s sub n with n approaching infinity. So you know, 1 or 2 and plus 1 approaches 0 as an approaches infinity, you get a huge number in the denominator, and the whole thing will approach 0. Will approach 0. So again, we got 1 minus 0 as the limit, which is 1. So this is another telescoping series that you need to handle it a little more steps to rewrite the general term in the series in two terms, or decompose it by partial fraction decomposition. All right. Has anybody learned the partial fraction decomposition before? Did anybody hear about that before? Can anybody hear me? Are you?
Yes, we can hear.
Yeah. Did you learn this before? Partial fraction decomposition.
It looked like I have.
Okay. Okay. Yeah. And if you learn that before, just review it and make sure you know what we did in here. If you don't, you can ask me and I can show you more details about it. Just feel free to ask questions. All right. You know, sometimes I may ask people to work it out. Okay, for these kind of things. Okay. Any questions about this page? No question. Then we just go to the next page. Okay. Let's do another example. This time we got another series. So this is not a telescoping series. We got all the terms of 1. So this. Okay. I guess I want to, I want to write S equals the sum of 1. Okay. But I put those together. But basically, this series is to add ones. Okay. Infinite numbers of ones. Each term is 1. So again, you just take the partial sum of this series. So you get S of n equals 1 plus 1 plus 1 plus 1 plus 1 to n copies of 1. So that would be n if we add those, because you have n copies of 1 to add, so you get n. So again, you just take the limit of this partial series sub n with n approach infinity. So obviously you take the limit of n because s sub n is equal to n, and then as n approaches infinity, obviously this sum approaches infinity. Okay, that's n itself. So this series diverges. All right. So we call it diverges if the sum of this series is infinite or does not exist. The limit does not exist. Remember, if the series converges, that means the limit exists. We got the finite number for the sum of the infinitely many terms. Okay. So that's a divergent series. We talked about some convergent series before, but not all the series are convergent, all right? Okay, now let's talk about the very important series that we use quite a bit, at least in our course, but in general, this is a very important series. It's called the geometric series. What the series is the general term of the series is a times r to the n. Okay, so here a and r, they are constants. What changes the n from term to the next? And remember, this geometric series start from 0 for n. Okay, not 1. So that's a little thing you need to pay attention to. All right. So you just add the terms of a times r to the n. When n equals 0, then you have the first term as a times r to the 0. R to 0 is just 1. Okay, any number raised to 0 power, you get 1. So a times 1 is 8. So that's the first term. And the second term will be n equal to 1. And start from 0, remember? So that will be a times r to the 1. So that's just a times r. And the next term will be n equal to 2. So you get a times r squared. And the next term will be r n equal to 3. So you get a times r to the third, and so on. So we want to add all of those terms. So how do we find this sum? It turns out that we can use a trick here, strategy. Again, and to add the partial sum, to get the partial sum. So we just add the first n terms of the series. So you get a plus ar times a times r squared plus a times r cubed up to a times r to the n minus 1. Okay, remember the first term you start n from 0, so the nth term will be n minus 1. Okay, it's not n. All right. Okay. So then, how do you find this sum? You can use formula to take the sum of this if you learned this before, but you can also easily find the sum by multiplying r on both sides of this s sub n. So we got the r times sub n on the left and the r times the whole sum on the right. And if we distribute the r on the left to all the terms in the parentheses, you're going to get a times r plus a times r squared plus a times r cubed. So each term we just get another factor, another exponent to add 1 for r, right? So at the end, you get a times r to the n minus 1 times r. So that become a times r to the n minus 1 plus 1. So that'll be a times r to the n. And the previous term for to that would be a times r to the n minus 1. That's exponent just increased by 1 from the term to the next. Okay, then you can take the difference between a sub n and r times a sub n. So you are going to get a plus ar plus ar squared plus ar cubed to a times r to the a minus 1. So that's a sub n. And then r times this one is just ar squared, ar cubed, and so on to a times r to the n, as we just did in the previous step. So you're going to see there are a lot of cancellation, just like the telescoping series we did. All the terms in between are canceled. And what's left? It's just a and a times r to the n. All those ar square, ar cube, all of those terms cancel. So on the right side, we got a minus a times r to the n. Okay, so if you rewrite this left and right by factoring a sub n on the left, you get a sub n times 1 minus r. Okay, remember when you factor out the a sub n from itself, we get a 1. And on the right side, you can factor a, so you get the 1 minus r to the n. Okay, I'm sorry, there's a typo here. There should be no a in the parentheses. Okay, so a sub n will be equal to a times 1 minus r to the n. Okay, again, there should be no n here inside parentheses over 1 minus r. Okay, so if you divide by 1 minus r on both sides from the previous equation, okay, that's what I get. So now we have to consider different cases, because when we take the limit with an approach infinity, as we want to get the infinite sum, we're going to get different results depending on the value of R in this expression. Okay, so for example, if the absolute value of R is less than 1, then if you raise R to the nth power and take the limit with n approaching infinity, you're going to get 0. So you just multiply a number less than 1 by itself infinite many times. So each time when you multiply the number by itself, it gets a little smaller, but then you multiply by itself infinite many times. So eventually you're going to get a 0 as the limit for this power. All right. So, and then in that case, the sum of the geometric series, which is just the limit of the result we got of S of n, right? So you just take the limit of R to the n in the expression, so you get 0. So in the numerator, we got a times 1 minus R over 1 minus R, but the R to the n is 0 as the limit. When you take the limit, it was n approaching infinity. So we get a times 1 minus a times 0 over 1 minus R, and a times 0 is 0. So you just get the a times 1 minus 0, which is a times 1 over a. So in the numerator, you get a, and in the denominator, you get 1 minus r. So the geometric series converges to 8 over 1 minus r. That means the sum of this infinite series is actually a over 1 minus r when the absolute value of r is less than 1. On the other hand, when r is greater than or equal to 1, the geometric series diverges. And this is easy to see, okay? And when you take the power of r to the n, if the absolute value of r is greater than 1, you multiply the number by itself infinite many times. Every time you multiply itself, you get a little larger, but you multiply by itself infinite many times. So eventually, this whole number, the power will have infinite as the magnitude. When r is equal to 1 or negative 1, then you can see, you're gonna get the we just did that for r equal to 1. You get when r equals 1, you get all the terms the same. A times r is a times 1, a times r squared, that's a times 1 squared, a times r cubed, that's just a times 1 cube, and so on. So they're all a, a times 1, which is the a. So you get all the terms a, and you add the infinite many copies of a. So that will also give you an infinity. It blows up the sum. And when r is negative 1, then you get a different situation. You're going to get a series with positive negative. Okay, so a times r will be a times negative 1, so you get a negative. A times r squared will be a times negative 1 squared, which is a times 1, so that's a. And the next term will be a times negative 1 cube, and negative 1 cube is negative 1, so you get negative again. So basically, that the series becomes a minus a plus a minus a plus a minus a plus a. So this is one of the examples we did before. You just get this series, this sequence, is just fluctuating, and when you add the sequence up, you get the number, back and forth. So there's no limit in that case also. So when the absolute value of r is greater than or equal to 1, the geometric series diverges. Okay, so you should have some idea in the mind that the geometric series converges only when the ratio r has the absolute value less than 1. Okay, so that's the geometric series. Let's do some examples of geometric series. You can use geometric series in many situations, and it's quite powerful. All right. So let's just find the geometric series of 3 over 2 to the n. Okay. So the first thing is to rewrite this series in standard form as a times r to the n, right? Remember? A times r to the n. And then use the formula to find the sum. So then you can easily write in 1 over 2 to the n as 1/2 to the n, and then multiply by 3. So that's the series we have in here. So if you compare this series with the standard form of a geometric series, you get equal to 3 and r equal to half. Remember, the general term has the form of a times r to the n. So a equal to 3 and r equal to half in here. So then you just look at the r equal to half. So it's less than 1. The absolute value of r is less than 1. So the series converges, and the formula for the sum of the series is a over 1 minus r. If you look at the, the conclusion here, the geometry comes to a over 1 minus r if the absolute value of r is less than 1. So the sum of this geometric series is just a over 1 minus r, which is 3 over 1 minus half. If we plug in 3 for a and half for r, so you're going to get 3 over 1/2, 1 minus half, which is half. And you get the 6 result. So the infinite many series of this geometric series is 6, the sum. Okay. Next example is the geometric series of 3/2 to then obviously uh, uh, already reading in the standard form of a times r to the n. So we don't have any number in front of this power, 3/2 to the n. So that means the number is 1. Okay, you can also use a 0, so r to the 0, okay, equal to 1. And r equal to 3/2, obviously that's the number to raise the power n. So 3/2 is greater than 1, so this series diverges. Okay. All right. So that's about the geometric series. We're going to see this series a little bit in some other applications, but let's just turn to another topic at this moment. So the next thing is called the nth term test for divergence. Okay. So you can use the nth term. You can just look at one term of a series and determine whether it's divergent or not. Okay. So what it says is, if a series an converges, then the limit of an has to be 0. So when you add the infinite many numbers for the series to converge, then the tail, all the terms in the tail, okay, every term has to have a limit of 0. All right. If you want the series, if you want the infinite many terms to add to a finite number, then all terms on the tail you add on the right, okay, has to approach 0, right? Okay. So that's easy to prove, but we're not going to prove anything here in this whole. I think in most of the cases we're not going to prove it, but that's just a easy conclusion. So if the limit of an is not 0, okay, if the terms in the series don't have a limit 0 as approach infinity, then the series has to diverge, okay, because otherwise the series, if it converge, then the limit of an has to be 0. Okay, so then you can just use this theorem to determine a series divergent. So what you do is just take the limit of an and see if it's 0 or not. If it's not 0, then obviously the series diverges. You don't have to, you know, to worry about that at all. You can stop. There's no point to start it. So let's talk about the one example in here. Find the series of 2 to the n, and from 0 to infinity. So in here the term a n is just 2 to the n. So if you take the limit of a n with n approaching infinity, you get 2 to the n. As n approaches infinity, obviously you multiply 2 by itself infinite many times, so you get a huge number, and it actually approaches infinity. The limit is infinity is not 0. Not only is not 0, but also approaches infinity. So, according to the theorem, the series diverges. Okay. Let's do another example. Find a series of n factorial over 2 times n factorial plus 1, and start from 1 to infinity. Did we talk about n factorial before? Yes, I think so. N factorial is defined as the product of all the numbers up to n starting from 1. So you multiply 1 with 2, 3, 4, 5 up to n, and that's called the n factorial. So in this example, the general term in the series is n equals n factorial over 2 times n factorial plus 1. So you can find the limit by using the technique we had before. What we do is we divide the factorial on the top and at the bottom at the same time for this fraction. So you get n factorial over factorial on the top, which is 1. And at the bottom, you get 2 times n factorial plus 1 over n factorial. Remember, you have to divide by n factorial both on the top and at the bottom at the same time. And then you can split the bottom of the denominator 2 terms, 2 n factorial, 2 times n factorial over factorial, and then the n factorial here just cancels, so you get 2. And the other term is 1 over n factorial. When you take the limit, n factorial will approach infinity. If you multiply 1, 2, 3, 4 up to numbers to infinity, you multiply all those numbers, so obviously you get a huge number, and then you divide 1 by that huge number, you get the 0 as the limit. Okay, the approach is 0. So the denominator is just 2 plus 0, and you get 1 on the top. So at the end, the answer is 1/2. So again, that's not 0. So the limit of an itself is not 0. So the series diverges. Remember, for the series to converge, the limit of the terms has to be 0. All right. Okay, so that's the other example. Let's talk about the term test again. Okay, so I just rewrote the theorem again, to review what it is. So that's the same theorem on this previous page. Okay. So let's talk about the series 1 over n. So here n start from 1 to infinity. Okay. So let's talk about the limit of an. An is 1 over n, obviously here. So as n approaches infinity, you get 1 over n, and that has 0 as the limit, because you get a huge number in the denominator, right? So again, we got 0 as the limit for this an of the terms in the series, but it does not guarantee the series of 1 over n works, because the theorem does not apply. Okay, it says if the limit is not zero, if the limit of n is not zero as n approaches infinity, then the series averages. But it doesn't say when the limit of n is equal to zero, what happens to the series, whether it's convergent or divergent. It doesn't say. So you cannot apply this theorem in this circumstance. So we cannot determine whether the series converges or not, or diverges, because the Angstrom test does not apply. Okay, so remember, it only tells you, the series diverges. It cannot tell you whether the series converges or not. Okay, so just keep in mind.